In this video, we are going to work on problem 4.3.1 from the textbook. In the first part, let f from R to R be a differentiable function. We have to prove that if the derivative of the function is bounded, then f is Lipschitz continuous. And in particular, it is uniformly continuous. And in the second part, we have to give an example of a function defined on the open interval from 0 to infinity, which is differentiable and uniformly continuous, but the derivative of the function is not bounded. Before solving the problem, let me recall an important concept. So a function f from R to R is called Lipschitz continuous if there exists a constant L that is greater than or equal to 0 such that the absolute value of f of x minus f of u is less than or equal to L times the absolute value of x minus u for all x and u in R. Okay, so from the definition, we're going to see the following. The absolute value of f of x minus f of u over x minus u is always less than L, and this is true whenever x and u are real number and x is not equal to u. Okay, so from here we see that if we look at the graph of the function, and this is x and this is f of x, and this is u and this is f of u. So we're going to see that the absolute value of the slope of the secant line connecting this point and this point is bounded by L. Now we are ready to work on the first part of the problem. So at first we're going to explore the hypothesis that the function, the derivative of the function is bounded. Okay, so since f prime is bounded, there exists a constant L greater than or equal to 0 such that the absolute value of f of x, actually f prime of x, is less than or equal to L for all x in R. Okay, and our goal is to show that f is Lipschitz continuous. So we have to link the slope of secant lines connecting any 2 points on the graph of the function with the derivative. So it reminds us of the mean value theorem. So we are going to apply the mean value theorem to prove that f is in fact Lipschitz continuous. Okay, so we fix any x and u in R where x is not equal to u. Okay, by the mean value theorem, there exists some c in between x and u such that the derivative of the function f at c is equal to f of x minus f of u over x minus u. Okay, so again, this follows from the mean value theorem. Now, if we take the absolute value of the left and the right hand side, we're gonna get this. Then the absolute value of f prime of c is equal to the absolute value of f of x minus f of u over x minus u. Okay, and as we know, this is true for all x in R, and in particular, when x is equal to c, the absolute value of f prime of c is less than or equal to L. So this is less than or equal to L. Okay, and note that the absolute value of A over B is equal to the absolute value of A over the absolute value of B. So from here we can multiply both sides by the absolute value of x minus u and get the following. So we're gonna see that the absolute value of f of x minus f of u is less than or equal to L times the absolute value of x minus u. Okay. Now, note also that in the case where x is equal to u, the left hand side is 0 and the right hand side is also 0. So this inequality is also satisfied. Therefore, this inequality is satisfied for all x and u in R. By the definition, f is Lipschitz continuous. After solving the first part of the problem, we have the following observation. Given a differentiable function from R to R, if the derivative of the function is bounded, then the function is Lipschitz continuous. And from the definition, we can see that if f is Lipschitz continuous, then it is uniformly continuous. So now we can ask the following question. If f is Lipschitz continuous, can we say that the derivative of the function is bounded? Okay, and the answer is yes. Okay, so this is a very good exercise. You can work it out at home. That means you can show that for a differentiable function from R to R, if f is Lipschitz continuous, then the derivative of the function is bounded. Okay. However, this is not true in general. Okay, so we can find some function from R to R which is uniformly continuous, but the derivative of the function is not bounded. Okay, and we are going to work on that in the second part of the problem. In the second part, actually, we only restrict the domain to the interval from 0 to infinity to R, but in general, you can also find an example of a function defined on R with the same property as well. Now we are ready to work on the second part of the problem. Let's look at the graph of a function here. We observe the following property. As this point is getting nearer and nearer the origin, the slope of the secant line connecting the origin and that point is getting bigger and bigger. Okay, so we can show that for such a function, the derivative of the function cannot be bounded. Okay, and because of the behavior of the function like this, we can show that it is actually uniformly continuous. Okay, and we can find out a formula for such a function. For example, f of x equals the square root of x will satisfy the required properties. So we consider the function f from 0 to infinity to R given by this formula. F of x is the square root of x. Okay, so first of all, we have to justify the uniform continuity of f on the interval from 0 to infinity. Okay, so first of all, since f is continuous on the interval from 0 to 5, say 5, okay, and this is a closed bounded interval. The function is uniformly continuous on that interval as well. F is uniformly continuous on this interval. Okay. Now we can easily show that if f is uniformly continuous on a set A, then it is uniformly continuous on every subset of A. We can prove that by using the definition of uniform continuity. Okay, thus f is uniformly continuous on this interval. Okay. Now observe that f prime of x is equal to 1 over 2 times square root of x for x greater than 0. And from here we can easily see that the absolute value of f prime of x is always less than or equal to 1/2 for all x in the interval from 1 to infinity. Okay, so from here again, by using the mean value theorem, we can easily see that this function is Lipschitz continuous on this interval, and therefore it is uniformly continuous on this interval. Okay, so then f is uniformly continuous on the interval from 1 to infinity. Okay, so we see that it is uniformly continuous on the interval from 0 to 5, and it is also uniformly continuous on the interval from 1 to infinity. So from there we can easily show that this function is actually uniformly continuous on the interval from 0 to infinity. Okay, so then f is uniformly continuous on the interval from 0 to infinity. Okay, and we also observe that the derivative of the function is not bounded on this interval. Okay, because over here the derivative of the function is 1 over 2 times the square root of x. So now if we let x be 1 over n for n runs in n. Okay, so f prime of 1 over n is if we use 1 over n over here, it is gonna be the square root over n over 2. Okay, as n runs in the set of all natural numbers. So as n approaches infinity, you can see that f prime of 1 over n approaches infinity. Therefore, the derivative of the function cannot be bounded. Okay, so at home you can work on an example of a function defined on R. Okay, so f is a function from R to R, and the function is uniformly continuous, but the derivative of the function is not bounded. Okay, so that's it for the second part of the problem.